Hello, everybody. We're at 19.2, page 531 to 535. So the first thing I want to do is I want to share my screen with you. Excuse me. I'm going to go into Clever. I'm going to go into where our book starts at 531. Okay. I'm going to play the recording for you. Okay, we are going down to the next one now.
Apparent cylindrical waves will interfere. For any Huygens wavelet produced in the top half, there will be another Huygens wavelet in the bottom half at distance of W2. That it will interfere destructively to possible appearance of Huygens wavelets interfere destructively at other rates. The screen is where of Huygens
Teachers and students, please pardon this interruption. At this time, we must conduct our monthly drill. This will be the evaluation and so teachers, at this time, you could please go over with your students that you have named what the evaluation would take for your classroom if we were to evacuate, and make sure they understand evacuation and fire drill procedures. I will make an announcement when the final drill has been completed. Again, we will not sound an alarm and we will not evacuate.
A comparison of a single slit diffraction pattern with a double slit interference pattern using slits of the same width reveals that the entire single slit diffraction pattern is covered by the narrow dark and light interference bands. Double slit patterns result from the interference of light from each single slit. The removal of the opening equation is the action pattern produced by the single slit. We use the same equations.
All right, next page.
Measuring the distance to the first dark band from the center of the central bright band, x1, it is better to determine the width of the central bright band, 2x1, as in the following equation. Width of bright band in single slit diffraction. The width of the central bright band is equal to the product of twice the wavelength times the distance to the screen divided by the width of the slit. 2x1 equals 2 now over w. Single slit diffraction patterns make the wavelength of most slits are 10 to 1. Get it? Describe the assumption that is made concerning W and L for the single slit diffraction equation. Figure 14. The width of the bright band in single slit diffraction is
All right, next page.
which means the space between the slits meters. Objects that what type of diffraction radius always exists
Teachers and students, thank you for your cooperation as we conducted our monthly fire drill. You may now resume regular schedule, and again, thank you for allowing the interruption.
Also makes them reuse. Diffraction radians produce the brightest spectrum. To create a diffraction pattern consisting of parallel bright and dark lines. The pattern is projected on a piece of metal that is coated the light from the laser produces a chemical reaction in neurons in the tube. The metal is then released in acid, which attacks the metal where it is not protected.
I am so sorry. I am going into tomorrow, so I will stop. So what I'm going to do now is we are going to go into the math section of this. So we are doing question number 16, 17, and 18. So let's look on the board because I have written it out already. And let's see what we're doing here. We'll do 16 first. So I am on page number 534. So it says a monochrome green light with a wavelength of 546 nanometers, followed with a single slit width of 0.095 millimeters. So I'm changing mine to scientific notation, and it says the slit is located at 75 centimeters, so I changed it to 0.75 meters. So I'm doing 2 times lambda times the length times the width, and that gives me 8.6 millimeters. Number 17, yellow light of a wavelength is 589 nanometers passing through a slit with a width of 0.110 millimeters and makes a pattern on the screen. The width of the central band is 2.6 times 10 to the negative 2 meters. How far will the slit be on the screen? So I took my 2.60 times 10 to the negative 2 meters. I multiplied that by 0.110 times 10 to the third meter and divided that by 2 times 589 times 10 to the negative 3 meter, which gave me 2.43. And then number 18 asks us, and it says the light of HE laser with the lambda is 632.8 nanometers fall with a slit of a width. A pattern is formed on the screen of 1.5 meters away of a central bright band at 15 meters wide. How wide is the split? So I did 2 times 632.8 times 10 to the negative 9 meter times 1.15 divided by 15 times 10 to the negative 3, which should give you 9.7 times 10 to the negative 5, which equals 97 millimeters. Okay. So there are your questions for the day. I'm hoping that helps.